vibrating sample magnetometer. We are basically using it for studying the magnetic properties of material. And as I said that if you are actually synthesizing a sample which has, let's say, nickel in it, iron in it, cobalt in it, it will definitely have some magnetic property. Okay? Keeping aside whether it's ferromagnetism or antiferromagnetism and so on. In case it has a magnetic property, we need to use some sensitive devices, equipment, and this is actually one of them. Okay? And it basically operates on Faraday's law of induction. Okay? And in Faraday's law of induction, which you have already studied in your lower class, you already know that it's basically nothing but a very good sets up a very good connection between the magnetic and the electric field. So electromagnetism is the heading, okay, and under that you might have studied Maxwell's equation and so on. And from Faraday's law, we know that if there is a change in magnetic field, it will basically produce an EMF. Okay? So there will be an electric field associated with it. Okay? And if I just probably I can just give a note here, okay. And this is again important to understand. Okay, in the magnitude of induced EMF. So if there is a change in magnetic field, EMF would be induced. That's nothing but potential. Okay, since it has unit voltage, it would have a unit voltage. Magnitude of the induced EMF in a circuit, okay, is proportional to the rate of change of magnetic flux. Okay. So if you just remember this, okay, d phi by dt, okay, that's the rate of change of magnetic flux across a circuit. Okay, so that's actually directly proportional to the induced EMF. What happens usually is that this particular property is actually used to find out the magnetic property of a material, or even if a material has got this magnetic property. Okay, and it will actually depend on how many turns are there, because if you are having a stronger field, you basically are going to get a different EMF altogether. Okay? So this is the relation that we already know, and then this is something which I should not explain. Okay, but then I think we should actually know it, because if we are doing any kind of research work based on magnetic material, probably if you want to study a magnetic material, you will be using such characterization as VSM. Okay? So VSM is a technique if you do to an institute like IIT Guwahati, which is near to us. Okay, it has that facility. It even has squid. Okay, we don't have it in our department. Okay, but if you are doing any kind of research in the department, if you're doing it under Boda sir, who works on magnetic material, then probably this is a technique that you would be using in your third sem or fourth sem, okay, for your project. But if you're studying the magnetic property, that's very important. Okay? So this is something which is already there, and it's very important. So I would suggest that whatever we are studying the theory, it's not that something which won't be used later. Okay, this might be used for your entire life. You are actually, if you are doing your PhD, and then probably you are teaching somewhere and so on. Okay, so that's important. So this is a del phi is the change in magnetic flux. Okay, and delta T is the change in temperature. Okay, so what happens is that this particular magnetic field, if there is a change, this will actually measure the this will actually give a change in the electric field, and that electric field can actually be measured. Okay, so the electric field, okay, can be measured. Okay, so this electric field can be measured, and how much is the electric field will actually depend on what is the change in magnetic field, and that actually, if we are putting out any sample in between there, that electric field variation can be understood, and from there we can know whether our sample has got a magnetic property or not. Okay, but that we will come back to that later. So the basic idea is the electric field actually can be measured, okay, and it can actually provide, okay, info on the magnetic field. Okay, so the idea is very simple. We are simply putting a sample under magnetic field, looking into the change in the electric field. Okay, so that's simple. So if we just look into the typical, if someone asks you what is the use of VSM, okay, it's basically used to measure, okay, it's basically used to measure the behavior of magnetic material. So that's very important. If a material is not magnetic, you are using a VSM technique, it's quite useless, right? So you basically are not concentrating on such kind of ideas. Okay. Let's just have a brief look on the working. Okay. I'll give you a basic circuit, okay, a basic schematics of how exactly VSM parts are placed. Okay, but I'd just like to talk about the working here a bit, not much. So what happens is you basically have the sample and you actually place the sample in a strong magnetic field. Okay, samples to be studied is placed in a constant magnetic field. Okay, in a constant magnetic field. And you know, nowadays you don't really need a magnet to generate a magnetic field. You can have an electromagnet. Okay, you can apply the electric field, have the magnetic field there, switch it off, the magnetic field is switched off. So you don't need to keep the device running for long period. Okay, apply current, get the magnetic field. When work is done, you just switch it off and keep the device aside. Okay, so you know that is something which is helpful, because if you keep a or magnetic field on for a very long time, it is neither good for the environment, okay, and it consumes a lot of energy for the system. Okay? So if the sample is magnetic, okay, now this is very important, that the sample should be magnetic. What happens is the constant magnetic field that we are applying, okay, okay, the will it will magnetize, obviously, if the sample is magnetic. So if I have iron, let's say you have a pin, okay, and you are placing it in a magnetic field, okay, you are using a magnet, putting it on top of it, you know, but slowly this iron will also actually have that magnetic property. So that means that is a way of magnetizing it. Okay, how much it can be magnetized depends on the material. So it's not that I have iron and then I have nickel, both of them can be magnetized in the same amount. That's not true, right? We already know that. So but if we actually keep it in a very strong magnetic field, the chances are that there will be this alignment of the uh, regions, okay, alignment of the electron spin, okay, and based on this, the magnetic property will actually be modified. So the constant magnetic field, okay, will magnetize the sample, okay, and how it will magnetize, aligning the, you know, this is something which is called magnetic domains, and you know this is actually divided into domains for para, ferro, and so on. Okay, and this is how they are defined, how they are divided. Okay, or the individual spin with the field. So a magnetic property of a material is basically nothing but a consequence of the spin property of the electron that it has. Okay, so this magnetization simply means that you are aligning the magnetic domain, or you are aligning the spin of the electron. Okay? Then what happens is, if there is such the case, then we will actually have a magnetic dipole. Okay, so you know the distance between the two poles, north pole and south pole. Okay, basically it will, magnets always exist in pairs. Okay, so that is basically nothing but there will be a magnetic dipole of the sample. Okay, will create a field around the same. So what happens is that you apply a magnetic field, the domains gets aligned and the spin gets aligned, and there will be magnetic dipoles which will be getting created in the sample. Okay, and that magnetic dipole will create a field of its own around it. Okay, and that field is basically called the magnetic stray field. Okay, so we have to understand the sequence here, and then we can understand it better. So now we have got a magnetic stray field because of the magnetic dipole that is being formed. Okay, now what happens is, you know, the name of the setup is vibrating. That means something should vibrate here. So what happens is, whatever magnetic field is getting applied, that is actually being moved up and down. Okay, so I will just give you a simple diagram to understand this. Okay, but before that, let me just write down the theory part. Now what happens is, as the sample moves up and down, so it is actually connected to a system which actually can vibrate up and down. Okay, this magnetic field, okay, is changing, okay, as a uh, function of time and can be sensed, okay, by a set of pickup coils. Okay. Now you see what happens here is usually when the sample basically moves up and down, you already have a stray field because of the magnetic application of the magnetic field, right? Now when this sample actually moves up and down, when the sample moves up and down, okay, what we have usually is just give me a moment. Hello. So what happens is as the sample moves up and down, uh, you basically have a change in magnetic field. Now, if you remember this, okay, uh, epsilon is equal to minus n delta phi divided by delta t. Okay, there should be a change in magnetic field with time. So what happens is if there is no change, you are not going to expect an induced EMF. That's what Faraday's law states. So that means I should continuously keep on changing the magnetic field. And that is why this is very important as the sample moves up and down. As the sample moves up and down, the magnetic field will keep on changing. Okay? This magnetic field is basically changing as a function of time. Okay? So this change will actually be sensed by a pickup coil. Okay? And these pickup coils will basically give you the information about the electric field. Okay? And how much that change is will be decided by how much the magnetic field the sample actually has. Okay? So let me just complete this. The alternating magnetic field, okay, will cause a electric field in the pickup coils, okay, as per Faraday's. Okay. So what happens here is that this will actually cause an electric field in the as per Faraday's law. So please understand why vibration is important. Vibration will change the magnetic field continuously with time, as a result of which you are going to get the EMF. Else you are not going to get any kind of EMF, okay? And that's why it's vibrating the world. So if I ask you an objective question on why this is vibrating, okay, you have to answer it in this way because that's per the Faraday's law. Okay. So the current I is proportional, okay, to the magnetization of the. So how strong is the magnetization of the sample? Okay, how strong is the magnetic property of the sample will actually decide how much we have the current in the pickup coil. Okay, so that is how we actually know the magnetic property. So even if there is a very small change in magnetic field, then you can have a very small current which might not be detected. So in general, any kind of devices which actually has got a small signal can still be used to understand the sample by amplifying it. Okay, so whatever we are studying in electronics, okay, where we are using amplifiers, okay, such circuits are actually used in these kind of equipments, okay, to amplify that signal and see that yes, there is a information which actually can be extracted from the sample. So this current, even if small, okay, is amplified by. There are a lot of devices. Okay, there is something which is called trans impedance. Okay, basically it depends on the impedance property of the input. Okay, amplifier. Okay, and there is also something which is called a lock-in amplifier. Okay, we are not studying this here, but we can remember this term. Okay, this is a lock-in amplifier that is basically used. Now I basically will have everything ready now, okay, and then what I do, I try to analyze the sample. Okay, so analysis, okay, gives how much uh, sample is magnetized. Okay, so if I analyze it, I know that how much sample is magnetized because it was placed inside a magnetic field. Okay, and how its magnetization, okay, depend on the strength of the constant magnetic field. Okay, constant magnetic. So this is basically the working of a vibrating magnetometer. So what do you do finally? You see that the result, the current and all, and you see that how much the sample is magnetized. If the sample is more magnetized, there will be more change in the magnetic field, as a result of which you are going to get more current. If it is less, you are going to get less current. Okay, and this magnetization will actually depend on the strength of the constant magnetic field as well. So that means you are actually applying a magnetic field, and you don't want to study the signal because of that magnetic field. That magnetic field is only used to magnetize the sample. So what we do is we take one reference, just like we do in optics, where it is the change because of only the magnet, and in the other one it's with the sample. And then you can subtract one from the other, and you can get the information. Okay. So what I'm going to do now is I'm just going to draw a block diagram. Okay. If you just look into the block diagram, I think it will be very clear. And this is the working. Okay, and that's important. So let's just look into the block diagram. So what we usually have is a vibrating unit. Okay, let's just take the entire page because we don't have to do anything else here. This block diagram would be important. Okay, I suggest all of you to please do it. Okay, for your exam purpose also. And whenever we are actually drawing any kind of block diagrams, etc., it looks to be very simple, right? But when we look into the real electronics, it's really complicated. Okay, so we have to understand that this block diagram is only for the basic understanding. When you go and stand in front of that real machine, probably it will become a bit more complicated. So we actually have the sample, okay, and maybe I will take some time to do it, okay. So everything that we are drawing, okay, I suggest all of you to please do it in a way, because see, I have taken the simplest of diagrams so that you understand. If you want to draw a complicated one, you'll definitely get it on the internet, okay. Then I think this is okay. And whatever I'm drawing now, this part is basically nothing but the part of vibrating, where we actually applying a magnetic field. So we have the magnetic field on the two ends. Okay, we are actually applying a magnetic field on this end, and we are actually applying a magnetic field on this end. I could have taken an image from the internet and pasted it, but I preferred drawing this for you. Okay, once. So just like optics, we actually have to take a reference, because one will be because of the sample, okay, and one will be because of the reference. So I'm just going to draw a reference here. So whatever I'm doing now is basically nothing but the reference part, okay. And I really suggest all of you to please make sure that you do it, okay. And then this will actually give me a reference signal, okay. So this is going to be giving me a reference signal, but then whatever signal I have from the reference, I need to just amplify this. That is very important, okay. Because sometimes what happens, the signal might be a bit low, so I will amplify the signal from the reference, okay, as well as whatever signal I get from my sample. So this box that I am drawing now, this particular box, is basically nothing but the lock-in amplifier. Okay? And once we amplify, we can actually have an output. We can have a system, we can have a processor, process the information, convert it into a human readable signal. Okay, so you can consider this to be a very simple idea of the diagram. Okay, so what we do is we are actually going to have the sample. So probably I should just first point out the sample. Okay, so this, okay, a lot of leveling needs to be done here. This is your sample. Okay, and I need to vibrate the sample, okay, up and down. So I will basically use this vibrating unit. So this is a vibrating unit, and making a vibrating unit is not very difficult. You can apply some frequency. So this is your vibrating unit. Okay. In general, when we say magnetic field, okay, we basically just can make a box and make a cross out here. That means we are actually applying a magnetic field. Okay. So if we are having a sample, we need to place it inside a magnetic field. So these are nothing but the magnets, okay, which are connected to a circuit which actually can be it is connected to a circuit, okay, which actually can be controlled. So this is basically nothing but the current that we apply. So this is, let me write it down as DC electromagnet electromagnet pole pieces. Okay. So we have got two pole pieces, and then we are actually having an electromagnet. Okay. Basically, we are applying electric field to switch on the magnetic field. So as soon as the magnetic field is switched on, we have the sample in between. We have the vibrating unit, which will actually vibrate, and it will change the magnetic field. And from there, I'm going to get the signal. Okay. So these are nothing but a magnetic field, and there is something which is called a search coil. Search coil which is connected. Okay. Search coil, it means that you are going to have a scanning kind of thing. You are going to have a magnetic field which will be circulated around it. Okay. So this is called a search coil. And then this is nothing but the signal from the sample. Okay. And here also we are actually having a connection where we are actually going to get the reference signal. Okay. This is your reference signal. So the reference signal is because of the field. Okay. And the signal from the sample from here will be basically because of the field as well as the sample. So if I can subtract this reference signal from the field, from the signal, so we have got signal, okay, which is nothing but reference plus sample, okay, and the other one is nothing but the reference. So this is just reference, okay, and if we subtract this gets cancelled. I get the signal only from the sample, right? And that is why a reference signal is put here. Okay. So I think this is not very complicated to understand. And then what is this? This is actually basically amplifying the signal. So I will. It's not only one amplifier. Okay. There might be a set of amplifiers here. So just for simplicity, it's in one block. Okay. Lock-in amplifier. Just name it as lock-in amplifier. Okay. And then whatever you have, you're basically going to read it in the form of a DC output. So this is your DC. Okay. So that's basically nothing but the block diagram of a VSM. Block. And when we talk about VSM, okay, VSM is actually one of the, if you compare the techniques for magnetic characterization of a sample, VSM is one of the cheaper techniques. Okay. The next technique that we are going to look into is basically called squid, and squid is actually a costlier technique. Okay, much more complicated than this. So this is your VSM. So what kind of question I might ask? Most of the times, chances are there will be a descriptive question from this. But then if you understand this, there can also be some objective questions like why there should be a vibrating setup for a VSM system. Okay, how do you explain it? You can simply say that VSM operates on Faraday's law of induction. Okay, and as per Faraday's law of induction, there should be a change in the magnetic flux so that there is an induced EMF. If it vibrates, then only we are actually changing it. Okay, so we apply a constant field and then we vibrate, so it changes, and as a result of which we are going to get a change in the magnetic flux and an induced EMF. So if you explain it this way, I think that should be enough for this 2-mark question. Apart from that, the probable question might be to explain what is vibrating sample magnetometer, how does it work, those type of things. Okay.